Assalamu alaikum everyone. Welcome to the last lecture on ME 204. The goal today is to solve a couple of problems on each of the concepts that we have discussed. We will be solving a couple of problems from the homework as well, homework 12 that is, so that you can have a good understanding of the material that we have covered. So let's start with the first question, which is on the adiabatic flame temperatures. So here we have been provided that a methane gas at 25 degrees Celsius, 1 atmospheric pressure, it enters an insulated reactor. So when you see the word insulated, you already know that we're looking at an adiabatic case, right? So there's no heat loss. Okay, so this methane gas enters an insulated reactor, which is operating at steady state, and it burns completely with X times 100% of theoretical air. Okay, and the air is also coming in at 25 degrees Celsius, 1 atmospheric pressure. So these are standard temperature and pressure conditions. Now, what does this X times 100% mean? Well, let's look at it. So here it says, the question says that we need to plot the adiabatic flame temperature for X ranging from 1 to 4 and assume ideal gas principles apply. So here what the question is asking us to do is that we need to basically calculate the adiabatic flame temperature for this particular case where methane gas reacts with different amounts of theoretical air, right? For the first case, where X is equal to 1, methane or CH4 is interacting with 100% theoretical air. Second case, when you change X to 2, it's interacting with 200% theoretical air. 300% theoretical air, and lastly 400% theoretical air. So we are just increasing the amount of air for the same quantity of fuel, and we need to see how does that affect the adiabatic flame temperature. Now here we're talking about excess air scenario, right? So basically we're looking at a situation where we're either going to have complete combustion in all cases, but as we keep on increasing the amount of theoretical air in there, we're just adding more excess oxygen and nitrogen on the product side. So that, from our understanding of adiabatic flame temperatures, we already know that the temperatures are going to go down as we keep on increasing X, right? So even before solving this question, we can sort of say that, okay, if this is my X on the X-axis, of course, going from 1 to 4, okay? So the flame temperature or the adiabatic flame temperature is going to peak up. Is going to peak at a value for X is equal to 1, which is 100% theoretical air, or the minimum air needed for complete combustion. Now, once we keep adding more air or increasing the value of X, you can say that the adiabatic flame temperature should go down. Now, we just don't know whether it's going to go down in a straight line or go down in a curve or whatever, but we know for sure that it has to go down. Now, let's see how it goes down, right? And the way to calculate this is basically by writing first the balanced chemical equation for the reaction that we're looking at. So what are we looking at? We're looking at the reaction of methane, CH4, with some amount of air, right? 100% or more theoretical air, okay? So theoretical air or air in general, we're considering dry air, so oxygen plus 3.76 nitrogen. So this is what we have on the reactant side. On the product side, of course, we're going to have CO2 plus H2O, right? Different amounts of these, right? Because we are going to have these two as the combustion products because the combustion is complete, right? And how do we know the combustion is complete? Well, we have not been provided with any exhaust gas analysis showing some amount of CO. And we have, from the question itself, we know for sure that there's no chance of deficiency of oxygen. There's enough oxygen, right? So for this, we can just go ahead and assume that the combustion is complete. So we expect to see some amount of CO2, some amount of H2O, and maybe some excess oxygen, depending on the quantity of air that we're using, and some nitrogen. Okay, so these are the different reactants and products that you can imagine. Of course, the quantities of these will be decided by doing the atom balance, right? So once you write down the equation, so the fuel plus air giving the products CO2 plus 2H2O plus some amount of nitrogen. So this is what we write for 100% theoretical air, right? Or theoretical air, that is. So this is the first thing that you need to write. How do you balance out this equation? How do you get the value of 2? Well, you just need to do an atom balance, okay? So once you do this, once you have this, what we are saying is that this is for 100% theoretical, right? But we also need to look at the situation where the amount of air is changing. So it's simply about multiplying x to this number 2 here, right? So we're just saying that, okay, instead of 2, we're going to write it as 2x, where x takes the value from 1 to 4. Okay. Now the key part is we're not changing anything to the amount of fuel. The amount of fuel remains exactly the same. The only thing we are doing is we are adding different amounts of air, or we are reacting the fuel with different amounts of air. And therefore, since we are adding different amounts of air, the combustion products, which are CO2 and H2O, will certainly remain exactly the same, because these depend on the amount of carbon and hydrogen that you have within the fuel, right? So this quantity will remain exactly the same. The thing that's going to change is the amount of nitrogen that you have on the product side, and also the amount of oxygen that ends up appearing on the product side. Now, again, how do I get this 2x minus 1 for oxygen? Well, I need to do an atom balance for oxygen, right? That's how I'm going to get it. There's no other way of doing that. All right, so this is the final equation that we're looking at. And here we need to sort of calculate the adiabatic flame temperature for this particular case. And then we can start by applying values of x of 1, x of 2, and so on. Okay, so the first thing here is to write down the equation for the adiabatic flame temperature, right? So for the adiabatic flame temperature, we know that the enthalpy of the reactants is going to be equal to the enthalpy of the product, right? So you could write NE HE, right? It's going to be equal to the reactant side NI HI. Okay. Now the enthalpy itself, we know it's composed of two parts. It's composed of the enthalpy of formation plus any change in the enthalpy that corresponds to the temperature at which the system is existing. Now here, we know that the reactants are all at 298 Kelvin, right? So, and 1 atmospheric pressure. So the delta H component for the reactants is sort of just 0. For the products, of course, you're going to have the delta H component because the products are not at 298 Kelvin, okay? They're at a much higher temperature, and we are actually trying to determine what temperature they are at. So how do we do that? Well, again, we just need to apply the enthalpy balance that we just discussed. So we're looking at enthalpy of products is going to be equal to the enthalpy of formation of reactants minus enthalpy of formation of the products. Why are we not writing delta H for the reactants? Well, as we just explained, the reactants are at exactly the standard state, 298 Kelvin. So there's no need to write it. Okay. Now here we have rearranged this equation to write the known amounts on the right and the unknown values on the left. Okay. We are trying to determine this unknown value. All right. So here it's just a matter of multiplying the delta H for each component with its number of moles. So for CO2 is just 1 mole. So we just write delta H bar CO2 plus 2 times delta H bar H2O, 2 moles of H2O, right? Plus 2 times x minus 1 delta H O2 plus 7.52 x delta H N2. So this is all, these are all the products, right? And depending on the quantity of X, we may have some amount of oxygen or we may not have any oxygen. Now this is going to be equal to the right hand side, which is enthalpy of formation of reactants minus enthalpy of formation of products. Okay. So what is enthalpy? So what are the different things we have on the reactant side? Well, we have 1 mole of fuel. So this is F naught dash for methane, plus we have some amount of oxygen and nitrogen. Now we know that the enthalpy of formation for oxygen and nitrogen is 0, so I'm not bother writing it. So now we just go to the product side. All right. So on the product side, again, we have CO2, H2O, and then some amount of oxygen and nitrogen. Again, oxygen and nitrogen is something that, you know, the enthalpy of formation is 0. So we don't have to bother writing them. We just need to write the enthalpy of formation for CO2 and enthalpy of formation, 2 times enthalpy of formation of water. Okay, so here remember the water is going to be in the vapor form simply because we're looking at an adiabatic flame temperature, and at very high temperatures, I mean, when you burn methane, the temperatures are going to be somewhere about 1500 Kelvin, and we're looking at 1 atmospheric pressure, so obviously it's much above the boiling temperature. So now the interesting part is this part on the left is the unknown quantity, and it's going to vary with the value of x, right? So if x is 1, you don't have any oxygen. You just need to take in the delta H for CO2, H2O, and N2, and then compare it with the value on the right. The value on the right is a fixed quantity. Okay, it's not going to change depending on how much oxygen you use. So it's a fixed quantity as well as a known quantity. You just have to plug in these numbers in here. Okay, so the way it's going to operate is that for each value of x, we need to do a couple of iterations, and we need to basically determine at what temperature does the left hand side become equal to the right hand side. The right hand side is going to be fixed. Okay, so we just need to determine the temperature at which this happens, and that temperature is nothing but the adiabatic flame temperature for that particular air fuel mixture. So this is something that we already did in the last class, right? So you know how to deal with it. It's just that it requires some sort of interpolation. Okay, so here again, you're looking at this particular scenario. So once you do the interpolation, let's say you start off with x is equal to 1, you find some adiabatic flame temperature. Okay, and you keep on changing it, and basically you keep on increasing the value of x. And as we already discussed before, the adiabatic flame temperature is going to go down, right? And the maximum adiabatic flame temperature is sort of obtained when we have 100% theoretical air. Any excess air is going to reduce the, it's going to dilute the products and sort of reduce this temperature, simply because we have the same amount of energy which needs to be distributed among a lot more molecules. Okay, so that's how it works. So that's on the adiabatic flame temperature. And now we will go and solve a couple of problems which are from your homework. Okay, so these have to do with the heating value. All right, so now let's look at this particular question. So here we need to determine the heating value for gaseous butane, right, C4H10, in kilojoule per kilomole of fuel and kilojoule per kilogram of fuel at 25 degrees Celsius, 1 atmospheric pressure. This is again the standard conditions, right? So we're trying to determine the heating value for this particular fuel in these two units, kilojoule per kilomole and kilojoule per kilogram of fuel, while assuming first the water vapor is in products and second liquid water is in the products. Now, when we say the water vapor is in the products, what we are saying is that we need to determine the lower heating value. Okay, and when the water is in the liquid form, then what we get is the higher heating value. Now, if you're not sure why this is the case, please refer to our last lecture where we discussed about the difference between the two heating values and how does it come about. All right. So now let's just apply the formula for calculating the heating value. So heating value per unit mole of fuel is simply equal to the enthalpy of reactants minus enthalpy of products, while both reactants and products are at the same temperature. And here, what is that temperature that we're looking at? Well, we're looking at 25 degrees Celsius, 1 atmospheric pressure. This is the temperature at which we would want to determine that. Okay. So here, since we're trying to determine these, determine the heating value at the standard conditions, the value of delta, the value of delta H would simply be 0, because we are not having either the reactants or products at any temperature apart from 25 degrees Celsius, right? That's the standard. We are operating at only at the standard state. So all we need is to get the number of moles and the enthalpy of formation for different species. Now the question is, what species do we need? Well, it's simply, you just need to write down the balanced chemical equation and then move on from there. Now remember, whenever we are talking about heating value, we know for sure that we look at heating value only for complete combustion. Okay, so we know that the combustion is complete. And if combustion is complete, what we know is that all the carbon is converting to CO2, all the hydrogen is converting to H2O. Okay, so this is a known thing. So basically, first we start by looking at the balanced chemical equation, right? So let's look at part A here. So we write down the fuel. Let's say consider 1 mole of fuel, right? So C4H10 plus some amount of air. So you say B times oxygen plus 3.76 N2. Okay. Now this is going to give us, let's say, C times CO2 plus D times H2O plus E times N2. Now, basically, just by doing atom balance, you'll be able to determine the values for B, C, D, and E. Okay, it's just the way we have done before. All right. So for simplicity, I'm just going to start up with writing the balanced chemical equation. So when you do all that balancing, what you get is something like this: C4H10 plus 13 by 2 O2 plus 3.76 N2. Okay, this is the theoretical amount of air, and this is going to give us 4 CO2 plus 5 H2O plus 24.44 N2. Now there is a very quick trick for determining how the coefficient for CO2 and H2O, and it's simply that when we just have CO2, we don't have any carbon in any other product on the product side, meaning there's no CO or no unburned hydrocarbons or something. Then all the carbon is getting converted to CO2, right? So if you have 4 atoms of carbon here, that's what we'll have here. In CO2, you just have 1 carbon. So basically you need to multiply it by 4, right? So this number goes in here. Same way for H2O, when we know that the combustion is complete, which is always the case when you're looking at the heating values. So all the hydrogen has to get converted to H2O, right? So here we're looking at H2O, which contains 2 atoms of hydrogen, and we had 10 atoms to start with. So it's just 5 times 2, so that's 10, right? So this number can easily be picked up just by comparing what fuel we have. Okay. So once you have done this and you have obtained the balanced chemical equation, now the question is about calculating the heating value. For the first case, we are calculating the lower heating value. We are assuming that the water vapor is in products, right? So first of all, what we'll do is we'll determine the quantity in terms of kilojoule per kilomole, simply because this is because the enthalpy of formation and everything is given in terms of kilojoule per kilomole basis. Okay. So what is the lower heating value? We said it's enthalpy of reactants minus enthalpy of products. Okay. So what are the reactants? Well, we have the fuel, of course, 1 mole of fuel times the enthalpy of formation of the fuel. So HF naught times C4H10, HF naught for C4H10, plus, well, we could just write the other reactants as well, 6.5 times HF naught for O2 plus 24.44 HF naught for nitrogen minus, now that's all the reactant side. Now we're moving on to the product side, minus 4 HF naught CO2 minus 5 HF naught H2O. Remember this here, the H2O is in the vapor form, so H2OG minus 24.4 HF naught nitrogen. Now the nitrogen HF naught simply gets cancelled straight away. You don't even have to remember that the enthalpy of formation for nitrogen is 0. But when you look at the table 825, which lists the enthalpy of formation for a lot of our substances, from here, you know that the enthalpy formation of oxygen is 0. So this term goes down to 0. What we are left with is the remaining terms, right? We just need to get the enthalpy of formation of the fuel, butane. We need to get the enthalpy of formation of CO2, and we need to get the enthalpy of formation of water in the vapor form. Okay. So let's look at the fuel. The fuel is butane, right? C4H10. So this is the enthalpy of formation that we're looking at. Now about CO2, well, this is CO2 right here. This is the enthalpy of formation that we're looking for CO2. And for water, this is again where you got to be careful. We need to look at H2OG, the water vapor form. Okay. So that's minus 241,820. This is the value that we need to take. So here I could just write lower heating value. All right. It's equal to minus 126,150 for the fuel, minus 4 times for CO2, right? Minus 393,520, minus 5 times of water, and water is minus 241,820. Okay. Now this comes out to be a pretty huge number in terms of kilojoule per kilomole. It comes out to be 2.65 into 10 power 6 kilojoule per kilomole. So this is one part of the solution done. We also need the heating value in terms of kilojoule per kilogram. All right. So here, for getting the heating value in terms of kilojoule per kilogram, we just need to divide the lower heating value in terms of kilojoule per kilomole by the molar mass of the fuel. Now, the molar mass of the fuel will be given in table 825 directly. This is the molar mass given for all the substances that are given in table 825. Let's pick up this number and you divide the lower heating value that we got here by 58.12. When you do that, you get the lower heating value in terms of kilojoule per kilogram, and comes out to be 45,716 kilojoule per kilogram. Okay, so this is simply the part done. Okay, this is all what we need to do. So how did we start? We start with a balanced chemical reaction, and once you had the balanced chemical reaction, you just need to get the number of moles from the reaction, right? So we take reactants minus products, and that's what you need to write. Job done. Okay. First you write the heating value in terms of kilojoule per kilomole divided by the molar mass and sort it out. The only thing you got to be careful is that you take the appropriate value for water. Okay. So this is part one done. Part two is pretty similar, right? Part two, the only thing that's going to change is that instead of taking water in the vapor form, we'll have to take water in the liquid form. That's the only thing that's going to change in part two. Everything else remains exactly the same. So you again start with the balanced chemical reaction. Okay, this is what we had, the same reaction. And in terms of the high heating value, it's going to be the same thing for enthalpy formation of the fuel as well as CO2. The only thing is we're looking at H2O liquid here because we're looking at liquid water in the product. So now we pick up this value, 285830. So again, you get 2.87 into 10 power 6 kilojoule per kilomole. It's certainly higher, right? That's why the name goes high heating value. And in order to get it in terms of per kilogram basis, you just need to divide it by 58.1. Okay, and that's all you need to do. Once you do that, this is the answer that you're getting. All right, so that's it. That's it for this problem. Now, this is a rather interesting problem where you had a simple fuel or single component fuel, right? Meaning you just had C4-Estane, one butane, which was reacting, and it was more or less not so tricky to get this part. Okay. Now, the question is, how do you calculate the heating value when you have a mixture of fuels, right? So let's see how do we handle that in this particular problem, which is problem 13.56 from your homework. Now we have here in this question, we have a natural gas with a molar analysis, 85% methane, 8.5% ethane, 2.5% propane, and 4% nitrogen. Now, why is it a mixture? Well, this is how it exists in the nature. Okay, if you go and find out the natural gas from beneath the Earth's surface, it's not going to be one component, but it's going to be a mixture, and the mixture composition is going to be different every time. So you got to be, from well to well, and of course, as you extract more and more gas from a certain well as well. So this is something that we need to consider here. We don't have one single component fuel; we have a mixture of fuel. And the question is, how do we evaluate the heating value for this, right? Here, we just need to determine the lower heating value in kilojoule per kilomole of fuel, as well as kilojoule per kilogram of fuel at, again, the same condition, 25 degrees Celsius, 1 atmospheric pressure, okay? So this is what we're trying to do here. And this is a very practical problem because this is a sort of a situation where you need to do. Now, if I say calculate heating value of fuel for butane, well, it's just one quantity. But when I tell you heating value for natural gas, well, depending on the composition, it's going to be very different, right? From one composition to the next. So it's something that you may have to end up calculating every time you're looking at a natural gas whose composition is changing. Okay. So now let's get back to the formula again. The heating value of fuel is simply the enthalpy of reactants minus enthalpy of products, with both the products and the reactants at the same temperature, which is at 25 degrees Celsius. Okay. Now, here, the only thing we need to do is we need to get the number of moles for each of these, okay, for the reactants and for the products. The other thing is always remember, whenever you're dealing with heating value, we already know for sure that the combustion is complete, which means that you know the combustion products, they're going to be CO2 and H2O. Okay, that's it. Of course, there will be some nitrogen that does not take part in the reaction, but from the fuel, the only thing that you're going to produce is CO2 and H2O. So now let's just make use of this molar analysis, and let's assume that we are starting off with 1 kilomole of fuel. Okay, for the purpose of writing the chemical reaction. So 1 kilomole of fuel, meaning that all of this 100% adds up to 1. So when we write it down, it comes out to be 0.85 times CH4 plus 0.085 C2H6 plus 0.025 C3H8 plus 0.04 nitrogen. This, all of it is fuel itself, okay? Plus now air, okay? So plus A times O2 plus 3.76 into. So this is fuel plus air, and this is going to give us B times CO2, C times H2O, plus D times nitrogen. Okay. Now the quantities of A, B, C, and D are something that you sort of determine from the mass balance. Now we're looking at the heating value. We know that the delta H is 0 because we're looking at 25 degrees Celsius and 1 atmospheric pressure. So for us to determine the enthalpy of reactants minus enthalpy of product, we can be a little bit smart about it. Okay. Now on the reactant side, we have methane, ethane, and propane plus nitrogen. We know that the enthalpy of formation of nitrogen is 0, but we anyway have the moles for nitrogen here, so it's okay. But here, when we look at the on the air side of the reactants, we know that the enthalpy of formation, HF0 for oxygen and nitrogen, is 0. So we don't actually have to bother determining A, right? Nor do we have to bother determining D, simply because, again, this is also going to get cancelled as the enthalpy of formation of nitrogen is 0. So if you want, you could go ahead and determine all A, B, C, and D. But if you want to be a little bit smart about it, you could just determine B and C, because that's all what we need. Eventually, the enthalpy of formation and the coefficients for oxygen and nitrogen are going to go down to 0. I mean, the coefficients will be there, but the values for enthalpy of formation are 0. So the terms will simply vanish. So it makes no sense to bother to calculate them. Okay. So now we just need to apply the mass balance, right? So from mass balance, we are trying to determine the quantities for B and C. Those are important quantities. So let's do the mass balance for carbon first. So when we look at carbon, we have 1 atom, or 0.85 times 1 atom of carbon from CH4 plus 0.085 times 2 atom of carbon from C2H6 plus 3 times 0.025 from C3H8. This is all what we have on the product, on the reactant side, and this is going to be equal to B on the product side, because it's just 1 atom of carbon and CO2, right? Now we have all the numbers we have on the left. When you add them up, the value of B comes out to be 1.095. All right, so B is obtained. Now what we also need to do is to determine C. So again, we do the atom balance for hydrogen. Now hydrogen, well, it's 4 times 0.85, right? Plus 6 times 0.085 from ethane, C2H6, plus 8 times 0.025 from propane, which is which is C3H8. And this is all the hydrogen we have on the reactant side. On the fuel side, it's, on the product side, it's 2 times C, right? 2 atoms of hydrogen and H2O and multiply it with C. That's all it's there. When you plug in the numbers and do the math, the value of C comes out to be 2.055. Okay. So now we have the number of moles that we need to make use of, right? All we did here was the balance of the chemical reaction. And now once the chemical reaction is balanced, we can go ahead and solve for it. Okay. So here, these are the B and C. Now let's write the equation again with the values of B and C, right? And let's move forward from there. So here, when we write the chemical reaction, it's going to be 0.85 CH4 plus 0.085 C2H6 plus 0.025 C3H8 plus 0.04 nitrogen. Okay, this entire thing is just the fuel. Plus A times oxygen plus 3.76 nitrogen. Okay, and this is going to give us 1.095 CO2, 1.095 moles of CO2 plus 2.055 moles of water. And here we're looking at water in the vapor phase simply because we're looking at the lower heating value. Okay, plus D times N2. All right, so now we just need to apply this formula, nothing else. Lower heating value in terms of kilojoule per kilomole is gonna be the mole times the enthalpy formation. Okay, so it's 0.85 times enthalpy of formation of CH4 plus 0.085 times enthalpy of formation of C2H6 plus 0.025 enthalpy of formation of C3H8. Now, of course, there's also going to be plus 0.04 enthalpy of formation of nitrogen plus A times enthalpy of formation of oxygen plus 3.76 A times enthalpy of formation of nitrogen. But we know that enthalpy of formation is 0, enthalpy of oxygen is 0 at the standard state, right, at 298 Kelvin and 1 atmospheric pressure. So we don't have to bother writing them, we can just cancel it out. Okay, so here for simplicity, for saving space, I could just not bother writing that. But you got to be, if you do this in the exam, you should mention that, right? Why do you cancel it out? The reason needs to be there. Okay, so this is all what we have on the products, on the reactant side. Nitrogen and oxygen do not contribute anything to the enthalpy of formation calculation. So now we can look at the product side. On the product side, we have minus 1.095 times enthalpy of formation of CO2 minus 2.055 enthalpy of formation of water in the vapor form. This is very crucial, right? You don't write water in the liquid form because we're looking at the lower heating value. Again, here is just a matter of picking up the numbers. For methane, well, this is CH4 here, we're looking at this number. Okay. Then for ethane, well, this is ethane is here, C2H6, we're looking at this number. Okay. For propane, we're looking at this number right here. What else do we have? We have CO2. All right. CO2, we're looking at this number right here. For water, again, we got to be careful. We're looking at the lower heating value. So we're looking at water in the vapor form. So H2OG. So this is the number that we're looking at. Okay. So lower heating value. Now you just have to plug in the numbers in there. And when you do so, the lower heating value comes out to be 854,428 kilojoule per kilomole. Okay. So this part was rather easy once you had the balanced chemical reaction. Now the interesting part is you also need to calculate kilojoule per kilomole of fuel. And here you cannot simply go back and pick up the molar mass for a particular fuel and then just do it, because here we don't have a single component. We don't just have methane, butane, or something. We have a mixture of fuel, mixture of gases, right? So here what we need to do is we need to actually calculate the molar mass for the mixture, okay? Because for getting lower heating value in terms of kilojoule per kilogram, we need to divide the lower heating value in terms of kilojoule per kilomole by the molar mass for the mixture. So we just need to go ahead and calculate that. Okay, so that's what we'll do next. So by the way, we don't have to worry a lot because we have enough information to calculate the molar mass for the fuel, for molar mass of the for the fuel mixture. Okay, now just to review, molar mass for the mixture can be written as simply the mass of the mixture times divided by the number of moles, or when you sort of write it down, it comes as simply a summation of mole fraction of each component times its molar mass. Okay, so here we have 4 components in here: methane, ethane, propane, and nitrogen. So the molar masses of the mixture is going to be equal to the mole fractions, which is this number here, because it's coming from the molar analysis. So it's 0.85 times the molar mass of methane. So you go to methane, get its molar mass. It's given here, okay? This is the molar mass given for everything, or for all substances that we care about. So 16.04 plus 0.085 times for ethane. Ethane is right here, so that's 30.07, okay? Plus 0.025 times propane. Propane is right here. This is the number that we're looking at, 44.09. Plus 0.04 times nitrogen, okay? Now nitrogen is given in table A25. This is a small part of it, so it's not shown here. But when you look at it in table A25 or even in table A1, the molar mass for nitrogen is 28.01. So when you add that up, the molar mass of the mixture comes out to be 18.537 kilogram per kilomole. Okay, so this is what we needed. So once you have the molar mass, so the lower heating value in terms of kilojoule per kilogram can simply be written as the lower heating value in terms of kilojoule per kilomole divided by molar mass of the mixture, which is in terms of kilogram by kilomole. Okay, so from the units you can see that what we eventually get is kilojoule per kilogram. So 854.428 divided by 18.537 comes out to be 46093.1 kilojoule per kilogram. Okay, so this is the lower heating value. All right, so this value is going to depend on what sort of fuel mixture you have. For this particular natural gas mixture composition, we got this value. If you add more methane or if you add more nitrogen, of course, things are going to change, right? So this is something that we need to sort of remember. So that's it for me. This is the end for this is the end of the syllabus. I mean, we already completed the syllabus before, but this also completes the homework problems that I wanted to solve. And that's it. So we have looked at a variety of different things in this course. We have looked at power plants, engines, jet engines, and also refrigeration and air conditioning. And lastly, we looked at how to put all this together through the evaporative cooling as well as the combustion process. So that's it for 2 of 4. Good luck for your exams and see you guys on Tuesday, inshallah.